Thank you for joining us. Perfect. Thanks, Anna. Thanks for joining us for our Heliophysics work speaker series. Um, we are normally doing professional development workshops where we're teaching you how to do hands-on activities. So these talks are a little bit different, where we get to hear directly from the subject matter experts themselves about the work they are doing around uh, space science, solar science, and heliophysics. So today we are joined by Cristian Ferradas, and I will turn it over to Anna to introduce him.
Awesome. Thank you, Claire. So I have the pleasure of introducing Dr. Cristian Ferradas he is a research scientist at the Geospace Physics Laboratory at NASA's Goddard Space Flight Center. And he's working in the Department of Physics, also at the Catholic University of America. He graduated from also the Department of Physics at the Catholic University of Peru in Lima, Peru, and received his PhD in space physics from the University of New Hampshire. His research focuses on magnetospheric physics and more specifically studies the interplay between the electromagnetic, excuse me, my light just came off, the electromagnetic fields and particles and particles affects the dynamics and the coupling of the plasma populations in the Earth's magnetosphere through the analysis of observational data and computer simulations. That is a mouthful, and Christian can tell you more about his research, so I'm going to hand it over to him.
Yeah, thank you so much, Anna, for the introduction, and thank you for the opportunity to speak to you all. I'm very happy to be here and to be able to share a little bit of what I do, what I study, which I think is fascinating. And yeah, it sounds like you are also interested. That's why you're here. So I just hope that we have a good time and you get to learn some new things, and hopefully I'll be able to answer some questions as well. So yeah, welcome and thank you for being here. And you can see the title of my talk right there, Earth's magnetic field, which is also our magnetic shield. And yeah, I just chose this title because I think that at the core of the Earth having a magnetic field is the fact that it acts as a shield. So we will talk about yeah, Earth's magnetic field today. But before we jump into it, I just wanted to start with a brief icebreaker for you. Um, so, which fact about space is your favorite? And all of these facts, as you can tell, they are related to the sun, since we are talking about the theme of heliophysics, which is the physics of the sun and how the sun affects everything. Here, I just wanted to, yeah, I just share these four facts that I think are interesting. The first one is related to the sun's state, which is a plasma state. And I find this fascinating. And you can read there. Second one is about the sun's magnetic field. Um, or maybe I'll just go ahead and read them. Like, even though we usually learn, fact number one, even though we usually learn that there are three states of matter, solid, liquid, and gas. At least that's what I grew up knowing. I was taught in school. 99.9% of the observable universe is in the fourth state, which I was not even told about, which is the state of plasma, which is the state in which the sun is. Another fact, second fact, sun's magnetic field. The sun's magnetic field, which fills the entire solar system, looks like a spiral. And this is due to the rotation of the sun. And that picture there, let's see if I can get my laser pointer. Can you see my pointer? Here. All right. So yeah, so this is an animation slash simulation of what this spiral would look like if we could see it. But this basically represents the sun's magnetic field, which literally is like a spiral filling the whole solar system. So I think that's really cool. Number three, the sun's core is the only place in our solar system where the temperature and density conditions are high enough for nuclear fusion to occur naturally. And number four, the sun's magnetic poles. So the sun's magnetic field goes through an 11-year solar cycle during which its magnetic field completely flips. The sun's north and south poles, they switch places every 11 years. I think that's also really, really cool. And if that were to happen on Earth, for example, I don't know what will happen with us. Things will get really crazy. But fortunately, does not happen on the Earth, at least not at that time scale. So yeah, feel free to put in the chat what your favorite uh, fact is, if you have a favorite one, or if you had heard about this, or if there was some of these that you didn't know. Oh, somebody learned number 2 yesterday. Oh, about the spiral one. Yes. Nat probably talked about that, right? Yeah, Claire says, yes, I really like that the sun's magnetic field is a spiral due to the sun's rotation. Well, I didn't know you could use a virtual laser point. Yes, you can. Oh yeah, Brooke says, I think it happens every few 100,000 years on Earth. Yes. So the poles in the Earth are also moving, although much, much slower than in the sun. Yeah. And I just learned number 1 right now. Yeah. I think most people don't know number 1, which I think it's really, really interesting that most of the matter in the universe is not in either solid, liquid, or gas state. And this says, didn't know 1 and 2. 2 is cool. Yeah, I agree. Michelle says number 2. Samantha says they might be giants, have a song about the sun being plasma. Yeah. Cool. Brooks is going with number 3 because the Earth's core is just so unfathomably hot and powerful. Like I can't even begin to understand how much energy. Yeah. 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 I know. Well, hopefully you learned something new from this icebreaker. I'm gonna move on because we have a lot of things to cover. So I just wanted to start telling you a little bit about me. As Anna said, I was born in Lima, Peru, in South America. You can see Peru in the world map right here. Um, so yeah, I grew up there. Actually, the bottom left picture here is a picture that has a lot of significance for me because this picture is of the Cieneguilla Desert, which is the desert that is just outside of Lima. Maybe you didn't know, but the coast of Peru is a desertic coast. The whole coast looks like this. And actually, Lima, which is the capital city, is the second largest desert city in the world, only after Cairo, meaning that, it's literally in the Peruvian coast, which is a desert. So I grew up driving from my home to this desert, which is the Cieneguilla Desert, which is really, really dry. Lima has a number of rainy days in a year, less than one. So it almost barely rains, which makes it really hard to, as you can imagine, to have water, right? Drinkable water, it's just water in general, because it almost never rains. Um, so anyway, the reason why this desert is very significant for me is because I grew up going there, like to camp. I would go there very, very often to camp, and the weather is very mild, so I didn't even need tents or anything. So I grew up stargazing there, and that's how my interest for space started. Actually, when I was stargazing there in those nights, which with these amazingly clear skies, you could see satellites moving all the time, shooting stars, everything you can think of that you would like to see in the sky, we were able to see here. Even the Milky Way, it was dark enough that you could see the Milky Way on any given night, pretty much. So it was just beautiful. So that's how my interest for space started. But anyway, I studied physics, as Anna said at the beginning. Then I moved to the US to start grad school. I did grad school in the University of New Hampshire, somewhere around here. So you can imagine the huge change that it was for me from these mild nights in the desert, sleeping under the stars, to snowy, cold New Hampshire. But I lived there for 5 years. I got my doctorate degree there. I loved it. It's a beautiful state. And then I moved across the country for my first job at the Los Alamos National Laboratory in Los Alamos, New Mexico, which was a little bit more like what I was used to in Lima, milder, but northern New Mexico also has seasons, so it was beautiful. I loved it there. That's where the Rocky Mountains begin, actually, and they start going north through Colorado and all the way through Canada. A beautiful place. So I started working there. I was there for almost 2 years. And then I moved back across the country to the East Coast, but now to Maryland, which is where I am currently working at the NASA Goddard Space Flight Center in Greenbelt, Maryland. And I really, really love doing outreach. I just like sharing the science that I study. And actually, the bottom right picture right here is me. Earlier this year, you might remember that was a solar eclipse in April. So I was doing outreach for that event in Niagara Falls. So this actually is a very cool building within the Niagara Fort, and there's a fort in just next to Niagara Falls. It's a very historical site because it belonged to the French and then to the British. And anyway, I learned a little bit about the history there. You can even see the wall painting there. But anyway, I was doing some outreach during the eclipse, just sharing with people everything about eclipses. So that's just a little bit about me. And now I want to hear a little bit about you and to maybe spark some discussion. I would love to hear in what ways are you incorporating heliophysics content into your library programs? So if you guys have there are any ways in which you're incorporating heliophysics content in your library programs, yeah, feel free to unmute yourselves and just say something, or use the chat as before. And even if you have not incorporated anything about heliophysics, maybe even that's also helpful to know. Hopefully, after these sessions, after these presentations, that can start to change. So yeah, please feel free to share any thoughts on this question.
Yeah, and as you all are thinking about that and answering in the chat, just a reminder, if you were a part of any of the StarNet solar eclipse activities for libraries, workshops, or any of the activities or kits that came out of that, we'd love to hear how you used those perhaps for the eclipses. And I'm going to drop a link in the chat. This is a activity for how to build a soda bottle magnetometer. We had a webinar about that back in September. So just kind of getting some ideas sparking out there for how to keep that excitement from the eclipse just rolling throughout the rest of this year, because this is the big year of heliophysics. And you'll learn a little bit more about why it's the big year of heliophysics later in Christian's presentation. But yeah, we'd love to hear from you. How are you celebrating the sun in your library programs?
Yeah, Brooks was saying, yeah, I bet the eclipse presented a very nice opportunity to talk about the sun. It's always like fascinating and uh, very helpful to start talking about the sun with people. Like everyone gets suddenly excited about the sun with an eclipse. But yeah, apparently sunspots are always a huge draw for programming. Huh. You can see them and they move every day. Yeah, fun thing for libraries to track day to day. Yeah, that's true. There's some very cool um, websites from NOAA. The one that I have in mind is from NOAA, where you can track uh, what's happening with the sun, what's happening with the aurora, what's happening with space weather in general at any given time. And then Andy says, we received two sunspotters with a grant and used them to show the April eclipse. Wow, that's really cool. Hmm. Yeah, I didn't know that. Almost every state library has solar science kits, but that's really cool. Maybe that's a very easy way to start engaging with people about the sun. So sun spotters, solar telescopes, activities, books, more. Yeah, solar telescopes, there are some that are very easy to make, and those are really, really nice as well to use. Michelle says we had the NASA solar eclipse glasses and materials. We did the one in October, at the park, and it was great. Yeah, yeah. The October one was also was different from the April one, but it was uh, very fun to watch. Cool.
And I did want to mention the slides for all of these presentations for yesterday and today are going to be available on our webinar archive page. So if you see any content or the really cool animations you're going to see later from this presentation, and you would want to use it in any type of program at your library, you do have permission to use these slides if you uh, come up with your own heliophysics programs in your library.
Yes, absolutely. Absolutely. All right. Well, before moving on, just a reminder that, if you ever need any resources, and I know that Claire and Brooks and, they have um, they make available a lot of material for you, for the libraries. But yeah, if, we can also provide any resources, we'll be happy to help with those, especially with cool animations. And um, you'll see some of the animations I'm going to share. They come from the NASA Visualization Studio, which is very helpful as a resource. They have a lot of very, very nice animations. But anyway, you'll see some of these in my presentation. All right, so let me begin. Um, Hopefully, um, you'll learn something new here. So the Earth's magnetic field, right? We're going to talk about three things about the Earth's magnetic field. First, we're going to talk about its shape. What defines it? Yeah, what brings about the Earth's magnetic field? Believe it or not every planet has a magnetic field. And actually having a magnetic field makes our planet very special and it's a very important feature of our planet. Next, we're going to talk about the magnetic field as a shield. So why do we say it acts as a shield? A shield from what? What is our magnetic field shielding us from? And finally, we're going to talk about the magnetic field and its effects. So what are some of the effects that come about from the fact that we have a magnetic field? Are they good effects? Are they bad effects? And we're going to talk a little bit about this. All right, so let us start with its shape. What defines it? Uh, so we have to start by mentioning, right, that the Earth is a giant magnet. I don't know how many of you have played with magnets, but it can be really cool, how it attracts and repels, depending on the charge of the metal, of the material. But when we think about the Earth, we rarely think of it as a giant magnet. And probably the reason is just because we can never see really on the everyday life the effects of the Earth being a magnet, right? But if we were to be able to see the magnetic field lines from the Earth would look something like this, right? You can see in this illustration of the Earth having a magnet at the center, and this magnet has two poles, right? A north pole and a south pole. So the magnetic field lines from the Earth leave the northern pole, which is actually here near the southern geographic pole, and they go all the way around like this to the opposite pole. So this is a 2D representation of the magnetic field lines, if what they look like, or at least what we think they look like, because we cannot see them again, right? But we can feel them, and we can explore the magnetic field in different ways. So this is just a 2D representation of what the Earth's magnetic field lines look like. But of course, it's more complicated than this, right? Because things, first of all, are not 2D, but we live in a three-dimensional world. So if we were to look at the magnetic field lines in 3D, in 3 dimensions, right, this is what they would look like. And you can see that they are azimuthally symmetric all around the Earth, right? We have this beautiful and very smooth magnetic field lines. But this is if space were empty, right? Many people, when they think of outer space, they think of it being empty. But actually, that's not the case, right? The Earth is not in an empty space. So contrary to popular notion, uh, space is not empty, right? There's a wind from the sun called the solar wind that is constantly blowing and shaping the Earth's magnetic field. So this is what the magnetic field looks like, due to the interaction of the Earth's magnetic field with the solar wind, which is blowing away from the sun, right? So you can see that towards the sun here on the right, the magnetic field is compressed, and away from the sun, right, it's elongated. I'm just gonna stop this at a given point. Yeah. Here, I think you can just get an idea how the magnetic field towards the sun, towards the left here, is compressed due to the incoming flow of the solar wind. And away from the sun, right, the magnetic field is elongated. And that's the region that we call a tail. And maybe yesterday, for those of you that were at Nat's presentation, he probably talked about this, right? How really the magnetic field has this almost like a teardrop shape, compressed towards the sun, elongated away from the sun. And that's what we refer to as the tail of the magnetic field of the Earth. But anyway, this is a more accurate representation of what the Earth's magnetic field actually looks like at any given day, because of the nice symmetric magnetic field of the Earth, but embedded and interacting with the sun's solar wind and magnetic field as well. All right. So that's a little bit about the shape of the magnetic field. But now let's see how and why we say that it acts as a shield, and it's a shield for us. A shield from what? Right? So when we think of the magnetic field acting as a shield, we have to start to talk about the sun, of course. right? The sun is our nearest star, and the sun gives actually rise to all the phenomena pretty much that we see in the solar system, right? Even life is possible because of the sun. The sun provides the energy that is required for life to be possible even on the Earth. But there are several features in the sun and that produce activity, and some of these activity can be harmful for us, and that's why we need shielding. So just two main features of solar activity are active regions, which you can see in this video here. This is a video, a compilation of images taken from the Solar Dynamics Observatory, as you can see down here. And so active regions, they look as bright regions in these pictures. So these pictures are taken in the extreme ultraviolet wavelength. So you probably have heard, or maybe you are aware, that we can take pictures of the sun on a variety of wavelengths. So in both these videos that I'm going to show, both are taken in the extreme ultraviolet. So active regions will look as very bright regions. On the other side, coronal holes, also, this is taken in the extreme ultraviolet. They look as dark spots, right? These are coronal holes, and you can see coronal holes here near the pole, and also coronal hole here. So these two regions or features that we can find in the sun, they are the source of a variety of phenomena. For example, I'm just gonna show some of these features or some of the characteristics of active regions and coronal holes. For example, if we start with active regions, these are places where the sun's magnetic field is disturbed. You can see here in the background these loops around these bright regions, and those loops, we believe they are following the magnetic field of the sun. So these are regions where the sun's magnetic field is very active. So as I mentioned, they look as bright regions in EUV images. And some examples of phenomena that come out from these active regions are solar flares, which maybe you have heard, these explosions that occur in the sun, coronal mass ejections, or CMEs, which is events where chunks of material are ejected literally from the sun's atmosphere or the sun's corona, and they travel in throughout the solar system and interact with the planets. And also out of these active regions, we can find large radiation, invisible light, UV, EUV, far ultraviolet, and even X-rays. So we have large emissions of radiation coming out from these active regions. And these active regions can lead to CME-driven geomagnetic storms. And we're going to talk a little bit more about geomagnetic storms. But so CMEs, they produce geomagnetic storms in the Earth. On the other side, coronal holes, they are regions of cooler and less dense plasma than the surrounding plasma and of open unipolar magnetic fields. That means that these regions give us access to deeper in the sun. So these are regions where the magnetic field from the sun is open. So what this means is that we have material coming from the sun directly in a more direct way from these coronal holes. And that's why, for example, one of the phenomena that we associate with coronal holes are these called high-speed streams, or HSS. These are regions that produced a much faster solar wind. Usually the solar wind is relatively quiet. I mean, I say relatively because the solar wind is very fast, like roughly 300 to 400 kilometers per second. But when we encounter these high-speed streams coming from coronal holes, the solar wind can be double the speed, like maybe 800 kilometers per second. And also, these coronal holes can produce geomagnetic storms, but of a different kind. And we're going to talk about that as well. So let's talk about a little bit about geomagnetic storms. What are geomagnetic storms? So a geomagnetic storm is a temporary disturbance of the Earth's magnetic field caused by a solar wind shock, right? So both of these types of activity in the sun that we just talked about, active regions and coronal holes, both of them can produce different types of geomagnetic storms. So in this animation here, actually this simulation, you can see how at the beginning we have the Earth at the center. These grayish lines represent the magnetic field from the Earth. And then you can see this, right? There's a boundary in red, and that represents the magnetopause, right? And the bow shock, which is the outermost layer, right? We could say of the Earth's environment. But at a given time, right, this red boundary is filled with, it just all becomes red, right? And that represents the arrival of this solar wind shock. A lot of material that has been ejected from the sun, either from an active region or from a coronal hole, but sometimes the sun will eject these shocks traveling throughout interplanetary space. And when they reach the Earth, they interact with the Earth's magnetic field and they disturb it. So let's talk about why it's disturbed and how it's disturbed. So when we, again, think about the Earth's magnetic field and the role that it plays, for a moment here, I want you to focus on the Earth, which is illustrated here, right? By now you know these lines represent the magnetic field from the Earth. And for a moment, just focus on this magnetic field line towards the sun, right? If we have the sun to the left, the magnetic field from the Earth in this region is pointing up or north, right? So the magnetic field facing the sun, which is, protecting us from the sun, is pointing northward. So the magnitude of a geomagnetic storm is in great part, determined by the strength and direction of the solar wind's magnetic field, right? So now you know that usually, the Earth's magnetic field facing the sun is pointing north. So what happens if the solar wind has a northward pointing magnetic field, like this, right? So if we have a northward pointing magnetic field from the sun, and it reaches the northward pointing magnetic field of the Earth, they will not interact or reconnect, as we say in physics, right? These two magnetic fields will not reconnect. And that means that the impact of such a solar wind with a northward magnetic field will be low. And this will not typically lead to a geomagnetic storm. But on the contrary, if the solar wind's magnetic field is southward and it's large, right? The southward pointing magnetic field is opposite to the Earth's magnetic field. So these two will reconnect, and in such a way that it will produce a storm. So this southward and large solar wind magnetic field will produce a high or a strong impact on the Earth. And this will most likely lead to a geomagnetic storm. So this gives you an idea of, again, how the shape of the Earth's magnetic field plays a role in protecting us, in shielding us, and how also it depends on the solar wind's magnetic field in its direction, particularly if it's pointing north or it's pointing south. That will determine the impact that such a solar wind will have on the Earth. All right, so let's talk about the effects now. So we've looked at the shape of the magnetic field, what it looks like. We've talked about what it shields us from, particularly how it determines if we will have a storm or not, how the interplay between the Earth's magnetic field and the sun's magnetic field, determine the impact that any solar activity will have on the Earth. But okay, what effects exactly are we talking about? Are these good effects, bad effects? So let's talk about the good effects first. And the short answer is there's both, right? There's good effects and there's bad effects. And these good effects is, we refer to when the space weather is beautiful, right? And probably the most clear evidence of our connection with the sun are these beautiful light displays that are called the the aurora, right? The aurora borealis in the north and the aurora australis in the south. And so when we think about the aurora, we have to, again, think about the sun, right? And in this animation, we'll see how we could say particles from the sun will reach all the way up to the Earth's magnetic field, right? Here we have a CME, a coronal mass ejection, reaching the Earth. We see how the field lines reconnected, right, with the Earth's magnetic field lines. And then all these particles get pushed along these magnetic field lines towards the Earth, right? Towards our atmosphere. So I'm just going to play it again. Um, and so first of all, we see again how the shape of the magnetic field plays a role, right? In what sense? Here we see how the particles that will follow these magnetic field lines, as they approach the Earth, they will be funneled, right, or directed towards the poles, right? Right there, you can see that all these particles coming from the sun only have access to the Earth's atmosphere near the poles. And that's why we only see the aurora near the poles, right? We have to go near, Scandinavia or Alaska in the north, or near the Patagonia in the south, to be able to see these lights. But what happens actually when these particles reach the atmosphere that produces these beautiful displays? So now we're going to see what happens next, right? When these particles reach the Earth's magnetic field, and now we're going to experience what these particles coming from the sun would experience as they travel, right? Imagine these are electrons that have left the sun, traveled along interplanetary space, reach the Earth's magnetic field, and they get again, funneled towards the poles, and they go down to the atmosphere. And when they are in the atmosphere, they will collide with just the particles that are sitting there in the atmosphere, like oxygen, nitrogen, atoms, and molecules. And depending on the type of particle of atom or molecule in the atmosphere that is hit by these incoming particles, they will glow in different colors, right? And that's why we have aurora in different colors, as you can see here on the pictures on the right, right? We have the green aurora, we have a purplish aurora, we have a red aurora, which usually is observable at higher altitudes because that's where oxygen dominates. So the particles, when they come and they hit the oxygen in that region, the oxygen will glow red. So anyway, we have all of these beautiful displays of different colors. And all of this is due to, again, particles coming all the way from the sun. That when they reach the Earth, they get funneled towards the poles because of the shape of the magnetic field. And when they enter the atmosphere, the different particles in our atmosphere, as they get excited, they will emit light in different colors. So this is when space weather is beautiful, right? And I don't know how many of you have seen the aurora, but actually we had a very, very large geomagnetic storm in May earlier this year, and the aurora was visible even down here in Maryland. So I got to see the aurora for the first time, which was really, really cool. Anyway, but space weather is not always good. It can also be bad, right? So in this picture here, you can see a variety of bad space weather effects, right? Bad in the sense that they can be harmful. So solar activity can have significant impacts on communications, for example, on satellites, on astronauts, and animals as well. So I just want to briefly talk about a few of these. So for example, solar activity can interfere with cell phones and GPS and other communications. And why is that? Well, that is because when our cell phones were antennas that use satellite signals, these signals have to travel through the conducting layer of our atmosphere, which is called the ionosphere. But the ionosphere is variable, and its variability strongly depends on solar activity, because actually this layer is actually ionized. It comes about because of solar radiation. The sun's light reaches our atmosphere and ionizes particles in this region. But when we have a storm, for example, this ionosphere gets very disturbed and varies significantly. So that affects the signal, every signal that goes through the ionosphere. So, for example, the solar terrestrial process that is responsible for this interference can be solar radiation in this ultraviolet or far ultraviolet or extreme ultraviolet wavelengths, or even soft X-ray emissions from active regions, like flares, for example. So when we have flares, we know that most likely that will lead to some interference in signal. Some other effects are related to satellites, right? Satellites are outside our atmosphere, so they are less protected, and they are exposed to particle radiation from active regions and also from coronal holes. So high energy particles leaving the sun from these two regions or features that we talked about can penetrate the satellite's shielding and create charge in all the electronic devices that they carry. So it can cause temporal or permanent damage on all electronics on satellites, because these particles are so energetic that they just literally go through the shielding. Another thing that we need to take into account, of course, is astronauts, right? So solar activity can threaten astronauts and high-flying airplanes as well with their radiation. And this, for example, is related to what we call solar energetic particles, or SEPs, radiation from active regions. So particularly when the sun is very active, these active regions will emit large amounts of high energy particles, and so astronauts, of course, are exposed to this. So that's where constant monitoring of sun's activity becomes very important, right? To be able to time periods when astronauts are outside the space shuttle, and also for high-flying planes as well. And actually, solar activity can also disrupt animal movements and migrations. For example, like many birds, like pigeons, bats, and even other types of animals like sea turtles, dolphins, whales. It's understood that they somehow are able to orient themselves using the Earth's magnetic field. So, for example, birds, when they migrate, they know immediately, independent on weather, on if they're able to see the sun or not. They're able to know which direction is north. So when, for example, during a geomagnetic storm, as you saw in that simulation, remember when the shock arrives and the magnetic field is highly disturbed, right? In those periods, and these birds can be disoriented because of course the magnetic field of the Earth has been disturbed significantly. So even animals and their activity, their movements can be affected by space weather effects. But fortunately for us, this near Earth space, where many of these space weather effects take place, is being monitored regularly. In this picture, you can just see what we call NASA's Heliophysics System Observatory. And you can see the whole army of satellites out there in different regions, right? Some of them inside, closer to the Earth, inside this region that we call the magnetosphere. And some of them are outside the magnetosphere in the solar wind, constantly monitoring the sun's activity, and also different phenomena that take place in this region. So yeah, we fortunately have these measurements being taken in real time all the time. So yeah, we can rely on this satellite information to be able to mitigate space weather effects. And yeah, that's all I have. So thank you very much for your attention. I think we have some minutes for questions in case you have them. And yeah, I just listed here 3 websites for resources for you, and also I will include this presentation in my website so you can access it there. Although I'm sure Claire and Brooks will make it available in some other way as well. So yeah, thank you.
Great. Thank you so much, Christian. Just fascinating stuff. We learned yesterday that Nat told us how when Starlink sent up several of their satellites. A large geomagnetic storm occurred at that same time, and damaged a lot of those. So this is a really great complement to that, to kind of like really visualize how that could happen. And those animations are phenomenal. I've never seen the Earth's magnetic field in 3D before. I've always just seen it in the textbooks, as that 2D representation. So really appreciate the
Right.
additional perspectives.
Yeah, yeah. I'm very thankful for these people doing these animations, because they're really, really helpful to visualize, this these regions of space and everything that takes place there. Yeah.
Yeah. Any questions for Christian? You can feel free to unmute yourself or ask your questions in the chat. Right, we
Uh-huh.
have a question. Does the
Yeah.
magnetosphere vary with different solar cycles?
Yeah, great question. So yeah, the magnetosphere varies with the solar cycle. So let me go back for a second here. Oops. Uh, so when we were talking about these two main features in the sun, active regions and coronal holes. Can't remember if I did mention, but active regions on the left, they are more, they occur more frequently near the maximum of the solar cycle when the sun is more active. And coronal holes on the other side, they are more common during solar cycle's minimum, when the sun is less active. So each of these two features, right, will produce different type of phenomena. So during the different parts of the solar cycle, right, during, for example, near maximum of the solar cycle, is more likely that we will have these types of events affecting us. And then near the solar cycle minimum, we should expect more of high-speed streams, for example. Now, in both cases, as you can see at the bottom, right, we can have geomagnetic storms, because both phenomena can produce geomagnetic storms. So we do have storms near the minimum of the solar cycle, near the maximum of the solar cycle. Although usually CME-driven storms tend to be larger and more severe than CIR-driven storms. So that's why near solar maximum, like we are right now we are very close around the solar maximum in its 11-year cycle. We're having more storms, and some of these storms already, at least four of them between last year and this year, have been very, very strong, very unique, stronger than usual. So yeah, we expect the magnetosphere to be more active and more disturbed around the solar maximum. Yeah, great question.
I also have another question if nobody else has anything. And I was going to type it, but it's taking too long to type. So what advice do you have for talking to the public about these solar flares that can cause disruption? Like you were saying, like, it can affect, like the Wi-Fi and like everybody's like communications and stuff. Like, how do you talk to the public without scaring them into being like, oh my gosh, now I have to like, have another thing to be scared of? Um,
Hmm. Yeah, good question. And actually, that's why I like finishing talking about all of these effects with this, just to remind people, um, that fortunately, right, we have the capability to put satellites in space. And that's precisely what we've been doing for the last around 60 years now, right? That space exploration has been going on, and we have to look at this army of satellites, right, constantly monitoring the sun. So I think this should bring us peace, some peace of mind, just knowing that we have measurements. We have satellites that are constantly looking at the sun, right? Everything that happens on the sun, and those satellites give us an advantage over, previous times when, people didn't have these resources and they suffered the consequences of some of the sun's activity. Like we have some in historical records in past even centuries of space weather effects. But fortunately now, we can know when something's coming our way from the sun and we can prepare, right? So I think these satellite measurements are providing very, very valuable information to us, to be able to prepare in case anything comes our way from the sun. And that's exactly what we do, right? For example, in May of this year, we had the strongest geomagnetic storm in 20 years. But we barely heard of any severe, damages or effects on us because we were able to prepare, right? We know we have reports of companies and people who need this type of information, receiving this information during the May storm, and they were able to adjust, taking whatever measures they needed to take to be able to mitigate the effects of space weather. So yeah, we see in the present all of this like playing its role, right? How the satellites, they are being effective at communicating us when something's coming our way so that we can prepare.
Great. I did read a fiction book earlier this year. If anyone is interested in just playing with fiction and what might happen, but there's a young adult book called The Big Dark by Rodman Philbrick, where there's a massive coronal mass ejection in the middle of winter for a community in the Northeast, similar to where you studied, Cristian, in New Hampshire, and it knocks everything out. All the power is out, and it's cold up there and very, very snowy, and it's just like kind of this kind of post-apocalyptic type of story. It is for young adults, so it's not that scary, but it's just like kind of a fun book to read. Totally fiction. I don't think that would happen, but it's just this author was, learning more about how the sun is impacting our satellites and our other things like that, and just took it into a story. So if anyone's looking for a fun story, it's called The Big Dark.
The Big Dark. Yeah, thanks for sharing. That reminds me of one of the other famous space weather events that occurred, happened in the 80s, I think, in Quebec, in Canada, where there was a massive power outage caused by a magnetic storm as well.
Oh, okay.
So yeah, I mean, they do happen, I mean, that was already what, like 30, 40-ish years ago. So now we have more technology, again, more satellites. We are hopefully better prepared. But yeah, we still need a lot to learn, and nature can always surprise us. But yeah, we have all these satellites these days that can provide valuable information.
Great. Well, thanks again, Cristian. I really appreciate you taking your time to share your work with us. We would love to see folks back at our next speaker series. That will be on December 5th at 2 o'clock Mountain Time with Vincent, the Aurora guy. So he's going to be digging more into that, the phenomenon of the auroras. So I will put that registration link in the chat. If you would like to register for that on December 5th, sorry, and share it with colleagues who want to geek out about auroras. But yeah, thanks everyone for joining. Thank you, Cristian, and thank you, Anna, for coordinating this. And we will have the recording and the slides posted on our StarNet webinar archive page. So just check back in a couple of days and you can access both of those. So. All right.
Yeah, thank you so much.